same set of bricks. So microservices are then a distributed system that needs to communicate, and that's why networking is really, really important.
Thanks, Flavio. So let's start with the simplest case that you can imagine. You have one single host, and you have containers on this host. And of course, you want your containers to be connected to the network. So the most really naive approach is basically to share the network of the host with the container. It's very simple. It works. It's not so safe because, of course, the container will have access to the network resources of the host, will be able to see all the traffic. And also, like, for example, if you do an if config from the container, you'll get to see all the interfaces that are on this host. So you might, so if somebody wants to do something nasty, then of course this is not very safe. Like somebody could, spoof traffic, or could change maybe the addresses of the interfaces. But this kind of scenario is used by somebody. I was talking yesterday. So if you don't have concerning, you use it? Okay, yeah. So if you have full control of the host, if you have full control of the container, and if the traffic doesn't contain any sensitive data, this is a valid approach because it's very simple and it works. Then this would be like a next step. So with some kind of isolation, this is the default configuration for Docker. So a bridge is created, Docker 0, and containers are connected to this bridge. As you might know already, containers that are connected to the same bridge, of course, can communicate between each other. And this Docker 0 bridge will get a default IP. And also a route is installed on the host to be able to reach the containers that will point through Docker 0. Now, like a very common case, like you might have a container that it's running a web server, and you want it to be accessible from the outside. An easy way to do that is basically to map one port of the host to the port of the container that you want to expose. Like in this example, we mapped the port 8080 of the host to the port 80 of the container. So you'll be able to reach the container from the outside. But yeah, if you have like thousands of containers on the same host, then of course this is not very scalable because we have a limited number of ports, so this won't work out. So let's move on to a more complex scenario, which is probably more real. Like you have more hosts and you have containers on those hosts. Like for example, in this case. So here we have 3 hosts and we have 3 groups of containers. We have the front-end network, the application network, and the database network. In this case, of course, you want to be able to connect container on different hosts. Like for example, container 1 on host A needs to be able to communicate with container 2 on host B. So we need to find a way to route the traffic from that it's meant, for example, for container 2 from container 1 host A, so it needs to go to host B and reach container 2. So we'll see in the next slides a different solution that enables that. And also another important thing is that you might want to segregate the traffic. Like for example, you don't want that the front-end network communicates directly with the database network, but you might want to allow the application network to communicate with the database network. So you also want to have this kind of flexibility to let different groups of container communicate while avoid that other groups of container communicate. And so here we have a very big host, and again we see that we have different groups of container, and it's again this idea of being able to segregate the traffic according to some rule that you might want to reinforce. And this is like the next evolution. You have a big host, then you have VMs running on it, and then you have the container running on the VMs. So here again you have the same problem that you need to be able to reach containers on different VMs. So you need to set up some routing so that the packets will flow correctly to the host where the container is. So let's see now this solution that enables that. For example, there are solutions that are based on routing. As the name says, the idea, of course, is to use routes and to use IP addresses. So it's every host has its own IP, of course, and then the containers that are on that host, they use the same subnet. So they are assigned the same branch of IP addresses. And then on every host, you install the routes that enables you to reach the containers that are on the other hosts. So let's see more with an example. Like you see here, you have two hosts. So on host A, we have all the containers that are on host A. They will have IP addresses in the range of 10.0.10. And on host B, I think that should be should be a different. Yeah, okay. So 10.0.10/24, and host A it's 10.0.9/24. Okay. So when you want, when container 1 is trying to reach container 3, the packet will flow through Docker 0. Then we will have a route on that host that says, if you're trying to reach network 10.0.10/24, just go through ETH0 and as next stop, use the IP address of host B. So the packet will flow through ETH0, it will reach host B on ETH0, and from there it's picked up, and since it will go to the container 3, so 10.0.10.8, it will go through Docker 0 because we have a route on host B that sends all the traffic meant for the container through Docker 0, and so we'll reach correctly container 3. Of course, with this scenario, you have to assign the IP addresses carefully, because if you have overlapping IPs between containers on different hosts, of course, that's a problem. And Calico, that is a product that takes care of networking for container, has an more advanced solution to be able to keep the routes up to date using BGP. That it's a protocol that you might be familiar with, that it's used by router to exchange routes and advertise new routes, so that new routes are shared between the routers. Sorry. So in this case, when a new container is created, a new route is added to the host, saying that that container is reachable on that host using the Docker 0 interface. In Calico, there's an agent running on every host, the Felix agent. So this agent will just look for every modification in the routing table, and when it sees a new route, it will advertise it using BGP. So all the other hosts that have this agent, and they will listen to this BGP advertisement, so they will pick up this new route, and they will add it in their internal routing table, so that in this way, when a new container is added, all the hosts, they will know how to reach it. And the way the packet will flow is the same as I explained in the last slides. So again, say container 1 wants to reach container 3, so the packet will flow through Docker 0. There we will have a route that says, okay, you're trying to reach 10.0.10/24, so you need to go through ETH0, and your next stop is the host B IP address. So the packet will get to host B, and then there will be a route that says, okay, you are trying to reach 10.0.10/24, so you need to go through Docker 0. And so we'll finally get to container 3. With Calico, you're also able to set up ACL. So you can have your custom rule to deny or allow traffic, and they do that using IP tables. This is Flannel. It's yet another project that does networking for containers. The idea is the same, so it's always a routing approach. Just the way to share the routes is a bit different, because in this case, they decided to use a key value store and etcd. So here, when a new container is created, then the network topology is updated in the key value store. And there are agents on every host. There's a Flannel process that just looks up for every modification that happens in the network topology. So when one modification happens, that means a new container is added or a container is deleted, this process will just pick it up and will add the correct route to be able to reach that container. And again, it's based on routing. So as I explained before, the host will have the correct routes to reach any container on the other hosts.
So recently, Flannel and Calico have decided to join together and create this project called Canal. That doesn't mean the two code bases are going to be merged into a single one. It just means that you can take some components from Calico and reuse them inside of Flannel. The most important aspect of that is Calico capability to implement ACLs, as Rosella said. So this is the core feature of Calico nowadays. And this is a project which is really in the early days. There isn't that much to say, because for months there has just been a logo inside of the Git repo. But it's really one of the most interesting projects out there for networking inside of containers.
Great. Okay, so let's see now another way of solving the same problem, that it's using overlay networks. You might be familiar with the concept. The idea is to create a virtual network on top of the physical one using encapsulation. So this concept, again, is not new. It's also used by Neutron in OpenStack, and it's used by other SDN controllers. And it works very well with containers too. So let's see now more in detail how that works. So let's imagine container 1 wants to reach container 3. So the packet will flow through Docker 0. And then on host 8, it will be encapsulated using some tunneling technology, might be VXLAN, some other project, they use a modified UDP that allow encapsulation. So as you see here, basically, the original packet is encapsulated, and as tunnel endpoint for this packet, we will set the IP address of host B. Because we know from somewhere we store the network topology. Not every product does it its own way, but we know exactly where the container are, in which host they are. So at the point of encapsulation, we can pick the right endpoint. So the packet will flow encapsulated, and it will reach host B. And at that point, host B picks it up. It will decapsulate it, and then it will see that it's going to container 3 IP address, and it will just forward it through Docker 0 to container 3.
Yeah, so all these networking solutions, as you have seen, they have to keep track of the network topology. To do that, most of the times they just use a key value store. So usually Docker used etcd, console, or Zookeeper to store this information prior to release 1.12. With 1.12 forward, they made significant changes to the Docker engine. So now the Docker engine is a key value store integrated inside of it. So there's no need to deploy an external key value store. Flannel, as you have seen, over than being able to be used both as overlay and as routing, it always uses etcd. And Wave, on the other side, which is an overlay solution, it's really peculiar because it doesn't need a key value store at all. They have a really smart way to keep track of network topology. So for the overlay backends, as you can see, Docker has a native support of overlay network, and this is implemented using VXLAN, while Weave and Flannel, they both can use VXLAN, or they can be used using their own protocol, which is backed by UDP. So usually VXLAN is faster than UDP because there's no need to go to user space for encapsulation and decapsulation. Also, there are some hardware devices that have native support and optimization for it. UDP usually, it makes it easier to add encryption, but to give you all the context, the networking solution built into Docker, it has encryption enabled by default. So when should you be using routing as opposed to overlay? So routing is really good because it provides you native performances because there's no encapsulation and decapsulation. It makes debugging really easy because it's like debugging normal traffic that you are accustomed to handle. On the other side, with an overlay solution, you have all this encapsulation and decapsulation which can have an impact on the throughput. And also the debugging is more complicated because you now see these bigger packets which have this inner frame, so debugging gets a bit more complicated. On the other side, with a routing solution, you need to have full control over the network fabric in order to deploy that, which makes that, for example, unsuitable for deployment inside of public clouds. Or if you want to do hybrid cloud deployment, it's still possible, but it's more complicated. On the other side, with an overlay network solution, hybrid deployments are easier, and you don't have to have this full control over the fabric. So how to use this project? So again, the container world is a bit complicated, so there are two standards in there. So there is one standard which was created and is carried over by Docker Inc., which is called Container Network Module, CNM. This is a standard that is then used by different projects, different vendors, to create networking plugins for Docker. So as I said before, Docker has its own overlay solution, which is built into that. If you want, you can use something different. For example, you can use Flannel, you can use Wave, you can use Calico together with Docker by just using the CNM plugin created by Flannel, Calico, and Weave, and so on and so forth. However, there is a really important caveat because starting from 1.12, Docker completely revisited how orchestration is done. As I said before, orchestration plays a really important role when dealing with networking and containers. Now Docker, starting from 1.12, has Swarm integrated inside of it. So if you want to use this new Swarm mode, you are forced right now to use their overlay solution. You cannot use Calico or whatever. On the other hand, there is the container network interface. This is a standard which was initially proposed by CoreOS when working on Rocket, and it has been adopted by other projects like Kubernetes, Cloud Foundry, Mesos. And again, by following this standard, all these projects can have plugins for CNI. So there is a plugin for Calico, one for Flannel, one for Weave, and so on and so forth. So you might think that now that we are able to link all the containers together, we can ping them, you might think that we are done, okay? But that's not the case, because when you deal with a distributed application deployed between different hosts, there are new sets of problems that you never faced before. So first of all, there's service discovery. So let's introduce some concepts. You have a producer, which is a container which is running a service. It could be, for example, a database, or it could be, for example, a web application which provides some backend service. And then you have a container which consumes this service. It could be a client trying to connect to the database, or it could be some web frontend which uses this backend to perform some tasks. So now the consumer has to figure out where the producer is located. And that means it has to figure out the IP address of the container. And depending on the network solution and the orchestration, it might even have to figure out the port number. In the cases we are going to talk about, the port number is not relevant, but let's see. So you have the container web running on host A, you have redis running on host B, and you have to figure out, practically speaking, from web 1 where redis is located. At the same time, all these containers, they are really cattle. Okay, I know you are already used to the concept of paths versus cattle with cloud, but containers are even worse. They come and go at any time. They keep moving everywhere because of different reasons. You are not in control of that because you delegate that to the orchestration engine. So what happens if you have your consumer, which is happily connected to the producer, and then something bad happens, and the producer is moved to another host? Now, at this time, the web application is broken because the web application is trying to access the database, but the database is now located somewhere else. Also, so you want to react to that and be able to connect, and it should keep working all the time. Also, what happens when, for example, this is a really bad example, okay? I mean, I picked up Redis because database is easier to imagine as a producer. But let's say that you have a backend application, like a web application, which takes an image and just returns that transcoded. It makes it smaller, I don't know. So there is a peak. You want to have more instances of this producer running, so you scale out them. Now you have your web application, which is consuming the service, but there are multiple instances of it. So which one should be picked? How can I deal with the number going up and going down? So how can we solve this problem? The first problem of service discovery, you might be tempted to use DNS because after all, this is what you have already been using your entire life. But this is not a good solution because, as I said before, containers really come and go at all the time, so they keep moving around. The IP address, they keep changing. So you would have to configure your DNS server to provide results with a really short time to live, like 0, that doesn't make the client take this, cache this result, okay? Because you want every time to figure out where it is. But then you will figure out that the world is full of broken DNS implementations on the client side that do not respect this TTL. So they keep caching, and they get broken because they keep looking for a service where the service is no more located. So this was the approach that was used by Docker with 1.11, where they updated etc host manually. Then later on with 1.11, they introduced an internal DNS. This is not really optimal. What people are using nowadays is to go back to a key value store. We still have it around. It's really useful. So why don't we just use the key value store as a sort of yellow pages? So as soon as you start a container which offers a service, you register, well, this container registers itself inside of the key value store. So it writes down that it is located at this IP address, it's on this port, and it provides this service. And then the client on the other side, it just has to look up into the yellow pages and figure out where the service providing the database or whatever is located. So there's some work involved in doing that. But again, if you're using an orchestration engine, all the steps are usually taken care for you. Plus, the orchestration engine also makes sure to inject into the running environment of all the containers some information about all the services which are available, like an environment variable. So if you are creating a microservice and you are, for example, following the directives of the 12-factor apps, then you're already reading, for example, settings from environment variables. So you're already done. So how do you handle changes, and how do you handle multiple choices? That backs up to the single solution. You could, again, do things on your own. Nowadays, you are all using load balancer, so why don't we just create a load balancer? We put all the different producers behind the load balancer. We just point the clients to the load balancer, and then the only thing we have to do is to keep the load balancer configured and up and running. So this is going to work, of course, but this is yet another piece of infrastructure that you have to maintain. You have to, again, I want to stress this out, containers, they keep moving around. So you have to really keep this load balancer up to date. And depending on how the load balancer is implemented, all these reload operation, they can lead to service disruption. All this load operation can happen because you are scaling up and scaling down, and the containers are coming up not at the same time. So this is not really an optimal solution. This is why orchestration engines like Kubernetes and Docker Swarm, starting from 1.12, they have this concept of service. So a service is a stable IP address which is unique. It doesn't change. It's there and stays there. You just have to point the consumer to this IP address, and then it will be this IP address that will redirect the request to the right container. The nice thing about that is that given this IP address is stable, you can add DNS on top of it. So you can keep using your broken DNS clients that keep caching stuff, because nothing wrong is going to happen, because all the DNS is going to point to this IP address, and this IP address is stable. So how does it work? Basically, as soon as you create your redis service, I'm trying to find, okay. As soon as you create your redis service, the orchestration engine will also create a virtual IP for the service. And you just have to point your client to the virtual IP, and then the virtual IP will act as a load balancer between all the different instances of containers that provide this service. So, technically speaking, there are IP tables rules in place that are going to take care of making this virtual IP address work. So are we really done? From a certain point of view, yes, but there's still one problem that we have to figure out. The problem is about handling ingress traffic. So now you have your application running inside of Kubernetes. They are resilient to failures. They can handle scale up and scale down. Everything is working fine. But the real question is, how can we expose this application to computers which are outside of a cluster? This is the ingress traffic problem. The Kubernetes approach is to define a new type of service. So this first one, called cluster IP, is the service I described before. So you have a virtual IP address which is inside of a cluster. It's consumable only by the containers which are running inside of a Kubernetes cluster. So on top of this virtual IP address, Kubernetes creates this node port, which is basically the cluster IP, plus on each worker that are the nodes running the container, on each worker, there's going to be a port. And this port is going to redirect the traffic down to the virtual IP address. I'm going to show you that in a nicer way with a picture on the next slide. So there is also the load balancer, which basically I'm going to talk to you about on the next slide, but it's yet another evolution on top of the node port. Docker with 1.12, it has the concept of services, as I said, and it allows you to solve the ingress problem by just using the publish flag. So when you do the publish flag, it works like the Kubernetes approach. So a port number on all the Swarm nodes is reserved, and all the traffic directed to this port number goes down to the container. So practically speaking, you have the internet there. Someone is pointing to his browser to guestbook.com, which is a container running in there inside of our Kubernetes cluster. So the traffic goes and it hits a traditional load balancer. From this load balancer, inside of this load balancer, we have a configuration. Someone created that, you created that, or in the case of Kubernetes, if you're running on top of AWS or on Google Cloud Engine, it can be Kubernetes itself that creates the load balancer as a service and configures that for you and keeps it up to date. So this load balancer then is going to redirect all the requests from guestbook.com to either this node or this node or this node, using maybe a round-robin policy or whatever you configured. And it's going to redirect always to this port number. So this port number here is 8080, but for Kubernetes, for example, is a really higher number, and Kubernetes is in charge of figuring out the port number for you to avoid clashes and that. With Swarm, you are the one in charge of doing that, and be careful to avoid clashes. So the load balancer redirects the traffic, for example, to this node. On this node, as you can see, there is no blue container running. Okay, but this is not a problem, because from this port, all the traffic is redirected to the virtual IP address, the one that we have seen before. And this one is going to look for a blue container inside of a cluster. So it's going to redirect, for example, the request to this one. So everything keeps working at all the times. If this container is moved down there, all the requests are going to keep working. If one node goes down, you have just to update the load balancer. If you want to update to scale out and add a new physical node, you just have to update the load balancer configuration to point also to this new node. So usually the configuration of the load balancer has to be changed only when you add or remove either a new service or when you add or remove a physical host. So to recap, there are several networking solutions for containers. They can be using a network, a routing approach, or an overlay approach. You have Flannel, which is pretty flexible. This is also why we are using Flannel as part of our offering, because it allows you to do both routing and overlay. It's really production ready and stable from our tests, and also from what the Kubernetes community already proved. And also there are different specifications, so that allows you to either use this product. You can use the solution both with Docker itself or with Kubernetes, for example. And please don't forget, it's not just about creating the network fabric. It's more. It's about service discovery. It's about handling all these changes and the scaling and how to actually direct traffic from the outside into your cluster. And this is all. Do you have any questions? Yep?
Does all of this stuff also work with IPv6?
In fact, some people said, why don't we solve all these problems using IPv6? Unfortunately, Docker at that time didn't have a good support of IPv6. I don't know how good the support is nowadays, but given that everything depends on the container engine to support IPv6, I don't think they are currently working really well. Yep. So, of course, this is my personal opinion. Maybe you are more expert on this topic, but if you go for a routing solution, the latency should be better as opposed to an overlay solution. And of course, all the magic of Kubernetes, of the virtual IP address and all of that, but yes, they introduce some latency, but I mean, given that you always have to balance the goods versus the cons, and the balance is definitely on the good side, so it's neglectable. The best latency, the best performances, you get them by reusing the host network, as Rossella shown in the beginning, but of course this is not something that can be used in most cases.
There's always a trade-off between, latency and flexibility. Of course, if you use the host network, that's very fast, but it's not very flexible. And as I showed, the routing solution is a bit better, but still not so flexible. The overlay seems to be the one that addresses most use cases, but yeah, it's a bit slower.
Yep.
So what about resilience against failure? So for instance, I mean, I see a lot of talk about key value stores, and that's probably very simple from a programmatic approach, but it's not really one of these things that are self-healing, right? So when a host crashes, then probably somebody or some tool needs to update the state in there, rather than say if you actually use something like BGP, that tends to heal itself after a while if something goes wrong. So how robust is all of that to the common things that are unfortunate incidents in the data center?
Well, probably I don't want to say the bottleneck, but the critical part of the whole infrastructure is the key value store, as you said. So you have to ensure that the key value store is deployed with the right amount of spare nodes to be able to resist to simultaneous failures of a certain number of these nodes. So the key value store, if it's working properly, from tests done at CD, from tests done by Google itself, and also by ISO tests done by other vendors, it can really scale to thousands and thousands of containers running, and it can keep track of all these containers coming and going. And of course, they figured out a lot of issues while doing this sort of stress testing. But I would say that it's acting pretty good.
Yeah, and also Zookeeper, that I think it's used by Calico, you said that.
No, it can be used by Docker on its own. Yeah.
Okay, yeah, like Zookeeper in terms of resilience, so it has its own way of electing a new master, so if you lose one node, it will just self-heal itself. So this kind of solution should be fault tolerant and resilient.
Yeah, they are strong, consistent, meaning that in the worst case, they will stop to allow you to write data inside of them, but you will still be able to read it, okay? Yeah. And when I said you have to have the right number is because until a certain number of nodes are up and running and they can elect a leader, then everything is working fine. And they can automatically heal from the sudden disappearance of one of their peers. Okay, so thank you very much.
Thank you.
We committed to Flannel.
Okay. So that would have been a neat final slide. This is we chose Flannel. We have a package now. It's available now. This is where we're going. That